This is Pre-Calculus section 2.8 notes. Hello, math friends. We have reached the last note section of chapter 2, and today we are going to be talking about one-to-one functions. A one-to-one function is a function where each x has exactly one y and each y has exactly one x. So in our first graph here, the question is this function a one-to-one function? And there are some key points there that are being identified on the graph. This point right here of -2, 4, and this point right here of +2, 4. So the question is it one-to-one? Well, notice that the y value of 4 has two different x values. So no, this cannot be one-to-one. The y value, y equals 4, has two different x values because we've got the ordered pair -2, 4, and we've got the ordered pair +2, 4. So no, this function is not a one-to-one function. We actually have a graphical test to test if something is one-to-one. You learned about this in Algebra 2. This is the horizontal line test. A function is one-to-one if no horizontal line intersects the graph more than once. Well, if we look at this picture now and we think about the horizontal line test, obviously if we draw a horizontal line, it's going to intersect our graph in more than one place. So we could say that this particular graph fails the horizontal line test, which means it is not one-to-one. So let's take a look at some other examples and determine whether these functions are going to be one-to-one functions or not. In example number 1, we have f of x equals 3x minus 4. Okay, we could easily graph this. This is just a slope-intercept equation here. So I have a y-intercept of -4. I'm going to plot that on the y-axis, and then my slope is +3/1. So I'm going to go up 3, right 1, up 3, right 1. And that's what my function f of x looks like. It's just a straight diagonal line in the coordinate plane. So using the horizontal line test, is this function a one-to-one function? Well, I could draw horizontal lines through this all day long, and I'm only ever going to cross it one time. So yes, this function is one-to-one. It passes the horizontal line test. Now let's take a look at example number 2. Example number 2 is an absolute value function. And if you remember from earlier in the chapter, we have the absolute value of x plus 2 inside the bars. So this +2 is an h value of -2, which shifts our parent graph, the absolute value of x, 2 units to the left. So my vertex is going to be right here on the x-axis, and then the rest of the graph looks just like the absolute value of x. So I have a slope here of 1/1 on the right-hand side and a slope of -1/1 on the left-hand side. So here's the graph of g of x, and now if I do my horizontal line test, you can already see what's coming. It fails my horizontal line test because any horizontal line is going to cross this absolute value function in more than one place. So this fails the horizontal line test. When we talk about inverses of a function and we want to know if a function is one-to-one, what about the inverse of its function? Well, if f of x is a one-to-one function, with a domain of A and a range of B, then its inverse, f inverse of x, has a domain of B and a range of A. Basically what that means is that the f inverse of y will be equal to x if and only if f of x equals y for any y value in B. In layman's terms, what this means is that if you have a one-to-one function and you have its inverse function, basically your domain and your range of your original function and your inverse function flip-flop. The domain of the original is the range of the inverse, and the range of the original is the domain of the inverse. Your x and your y values flip-flop. So let's take a look at the example. It says find the inverse of function f of x. For example 1, and f of x is 3x minus 2. So when we're finding an inverse, and you should remember this from Algebra 2 because we did this quite a bit, your first step, we're gonna rewrite f of x as y, and then we're gonna switch x with y. We are literally going to switch their spots in the equation. And then our second step is we're going to rearrange the equation again so that now our equation looks like y equals. So we're going to rearrange our equation by solving for y. All right, so let's try it. Our first function here, f of x, we're going to rewrite as y equals 3x minus 2. We haven't changed anything yet. Now we are going to switch the positions of x and y. So this is going to be x equals 3y minus 2. And now we're just going to do the algebra to solve for y. So we're going to add 2 to both sides. So we have x plus 2 equals 3y. And then we're going to divide everything by 3. So divide by 3, divide by 3, divide by 3. So this gives us a function of y equals 1/3 x plus 2/3 if we write that in slope-intercept form. Our original function, f of x equals 3x minus 2, that would be a straight diagonal line in the coordinate plane. That's 1-to-1. And its inverse, which is also a slope-intercept equation, y equals 1/3 x plus 2/3, is another diagonal line in the coordinate plane, and that's also going to be a 1-to-1 function. Now let's take a look at example number 2. Here they're putting a little caveat on the domain. They're saying that x has to be greater than or equal to 0. We're going to find out why in a moment when we do the math to find our inverse. First, we're going to replace f of x with y. So we're going to write y equals x to the 4th power plus 2 all divided by 3. Then our second step is going to be to switch x with y. So now we're going to write x equals y to the 4th power plus 2 all divided by 3. And now we want to get y alone. So since the entire right side of my equation is being divided by 3, I'm going to undo that by multiplying both sides of my equation by 3. That's going to be my first step. So I'm going to multiply everything by 3. And that, when I do that, that's going to give me 3x equals y to the 4th power plus 2. Now if I want to get y alone, my next step is going to be to subtract 2 from both sides. So then I'm going to have 3x minus 2 equals y to the 4th power. And now, as you know, if you want to undo a power, you have to use a root. So I'm going to take the 4th root of both sides of this equation to undo the 4th power. Now when I do that, I end up with y equals the 4th root of 3x minus 2. And I've got that, because I had that x is greater than or equal to 0, now I'm going to have this y is greater than or equal to 0. Because some of you may be thinking at this point, well, if you took the fourth root, that's an even root. Don't you need to put a plus or minus in front of the in front of the root? Normally you would, but because we had that x is greater than or equal to 0, when we find the inverse, remember x and y switch places. So that tells us y is greater than or equal to 0, so that tells us that really we only have the positive half of this radical. And this is going to be the inverse function of our original f of x. Okay, that x is greater than or equal to 0 tells us that we're only going to have half of a parabola. And when we graph the inverse, once again, we're going to only have half of a parabola. And that's what's going to keep this a function versus turning it into a relation. So how do you verify that two functions are inverses of each other? We have this inverse function property. It says, let f of x be a one-to-one function with a domain of A and a range of B. Then the inverse function, f inverse of x, satisfies the following cancellation properties. F inverse of f of x has to equal x for every x in the domain A, and f of f inverse of x has to equal x for every x in the domain B. That sounds pretty complicated, but what that means is if you compose the two functions together, so in this case, in our next example, we have f of x and g of x. If we want to test to see if these two functions are inverses of each other, we need to do the two compositions. We need to do f of g of x and we need to do g of f of x. And if they both turn out to be x, that is our proof that the two functions are inverses of each other. And this is something that we did in Algebra 2 as well, so this should seem familiar once we start going. So f of g of x means that we're going to take our g function and we're going to plug it into our x function. So for the first one, we're going to take this x plus 5 over 2 and we're going to plug it in right here for our variable in the function. So f of g of x is going to be equal to 2 times x plus 5 divided by 2 minus 5. Okay. Well, if we follow Pemdas for simplification, the first thing that's going to happen here is our 2's are going to cross out. So then we're going to be left with x plus 5 minus 5. So then the second thing that's going to happen is our 5's are going to cancel out and we're just going to be left with x. So that side shows that this property is true. Now let's take a look at the composition the other way. So now we're going to take f of x and we're going to plug it in for x in g of x. So g of f of x is going to look like, on the top of my fraction bar, I'm going to replace that x with 2x minus 5 plus 5 all over 2. Well, according to Pemdas, in the top of my fraction, that negative 5 and that positive 5 are going to cancel out first. So then I'm left with 2x over 2, which then my 2's cancel out, and I am left with x. So there we have it. Since f of g of x is equal to g of f of x, which is, they are both equal to x, then f of x and g of x are inverses of each other.